Good afternoon. Thank you. Thanks everybody. It's a great honor to be here to present our work about large-scale 3D reconstruction. So I'll start from the motivation in surveillance. As you can see here, right now in the security room of the video surveillance, you can see a bunch of these monitors. Depends on how large the site you want to survey. If it's a very large site, you might need maybe 100 monitors because for large buildings. So when you need to track a target, you need to follow from one monitor to another, and then you need to jump around the monitors to follow one person because one camera only catches limited area. So what we can use 3D to help this to help, I mean, at least save some money on monitors is to reconstruct the site in 3D, and then what we did is we integrated the tracking results. So we have 3D coordinate system, and we transform the tracking results coordinates into the 3D coordinate system, and then we integrate and put those tracking target peoples in those 3D things. So in this case, you only need one monitor. So if you want to follow some people, you just drag your mouse and rotate and navigate to follow, and it's mental saving. So here's our experiments on 3D surveillance. So we can you can view, because it's a 3D model, you can view from any angle, from top down, and print out the trajectory, and you can view from any angle. So this is an experiment we did at Schenectady in New York. It's a street corner, and with the collaboration with the Schenectady Police Department. Okay. And here's an indoor experiment about the tracking result integrated into 3D. So 3D model can help in video surveillance. So the problem is how we can get a good 3D model. Currently, there's the two major things. First is laser scanning. It's an easy method. You just use a laser and scan the place. But the problem is the equipment are really expensive, especially for outdoor, for large scale. So some cheap method is to use 2D images. Everybody has a camera, so you take a bunch of cameras and reconstruct it. So it's a very popular hot research topic in last decade, and this work is the build Roma in one day, and they take images from internet and they build the very large scale Rome cities. And based on this work, and scientists propose multiple stereos to dense the point cloud. So this is the dense stereo result. So basically, it's a very popular method. Basically, it works by detect features and then match the feature points, which feature match which, and based on the match correspondence, we can find the triangular relationship to recover the 3D location, the depth information, and there's a lot of work based on that. For example, Visual SM is very easy to use to reconstruct the model. But the problem of this method is that because it always starts from two images and incrementally add new images. Whenever we add a new image, we need to pairwise this new image with all of the previous images. So the time complexity goes quadratically. So for example, the build Rome in one day paperwork, they use a cluster with more than 300 core, and it takes about 1 day for this much of images. That's 3. And even though right now they have GPU implementation to improve the speed, but it's still very time. If the image number grows really large, it's really time consuming. For example, on a relatively fast personal computer, an average time of do one image matching is about 0.08 seconds. So with 10 image, 100 image, or 1000 image, it's an easy case. So a couple of minutes you can done. But let's say 100K images. Just image matching, it will take 12 years. So actually 12 years later, maybe the building is not exist. So we don't want to. So our work is to aim to reduce the image matching time. So starting from 2014, Dr. Furukawa proposed on CVPR to use divide and reconstruct, because actually if the image is taken at here, it doesn't make sense to match this image with the image taken at here. So divide the same and take those images and reconstruct as small models and then merge them together. So based on this proposal, there's okay, so basically we have a bunch of images and divide it into clusters and reconstruct several models, we can call it individual models for each cluster, and then merge it. So based on this, so something like this. So basically, okay, so this building is from our campus, SUNY Albany, and it's it's probably the largest teaching building in the world, because it's a podium and it's composed by 13 teaching buildings. So it's a large building anyway. So so we divide it into 8 clusters. The number is not restricted to 8. You can divide it into several based on what you like. And divide, it reconstructs models and put them together. But the problem is when you reconstruct them separately, that in virtual coordinate system. So if you put together, it will look like this. They're different in scale, rotation, translation. So we need to find a method to merge it. Okay, so in 2014, the ACC will merge it based on the camera rotation and translations, because when you do the reconstruction, you get the camera and translation rotations, and then you can estimate. But as you can see, if the cameras and the number is not enough, you can generate some error. For example, the top part is a little bit tilted, and the human vision actually are very sensitive to this kind of even the floor is very small, but the human vision is still very sensitive for this kind of. And another working as CIF 2015 is to base the assumption is that the building is always square building Manhattan world, so it's always the corner is always 90 degrees. So it's kind of like play Lego toy and to put them together. But this problem is sometimes it can generate ambiguity, because if you put these two words, the two side words in the wrong place, actually it's also satisfy the geometric constraints. Okay, so merge. So we can say merge actually is not that easy, as Dr. Furukawa said. Because human vision are very sensitive to small gaps. So what we propose here is we use some duplicated anchor images through into the adjacent clusters, How it works is because when we do reconstruction of this anchor image with this cluster, these features contribute to these 3D points. And when we do 3D construction of this anchor image with this cluster, this feature corresponding to this point. There's two points in 2 clusters, but they corresponding to 1 feature. So if we can find this, there's more details illustration here. So this is a reconstruction of 1 supermodels, and this point corresponding to the anchor image feature point. And when we do this reconstruction, these points corresponding to these feature points. So for example, the image here is the same feature corresponding to points, and these 2 points has different coordinate system, but they are corresponding points. If we can find a bunch of these corresponding points, we can do a rigid transformation estimation to estimate out the rotation and translation scaling difference, and then with that we can merge these 2 models after transformation. And to improve the results, we use a Ransack procedure. Basically, we randomly select some points and estimate out and apply to all the points to find error, to subtract and find error. We use the translation generate the smallest errors. So the experiment will looks like this. So originally without transformation, after transform, we can merge them together to a final result. And because we divide it into clusters, and the matching time largely reduced. For example, for this experiment, for the podium experiment, if we do not to divide and conquer, the projected time will be close to 27 hours. But if we divide them, and all of the matching time are just 4 hours 38, and as we can see, the structural motion actually take very less time, and the dominant part is the matching time. So if we reduce the matching time, the total time will be largely reduced, and actually the advantage will be more apparently with more images, because the quadratic glue. So in this example, we will show the track field experiment. This also reduced about close to 7 times of the time. So, but there's a problem about loop closure, because even though we transform those models sequentially around, and the adjacent place can you can maybe sometimes you cannot notice by raw eyes about the error, but at the end, the loop might close very well. So here we use another Ransack procedure, because we found that for this model, if we transform it to the coordinates of this and transform and keep transforming to back, it should be transformed to itself. So with this constraint, we can, so this one, after a sequence of transformation, it should transform to it back. For example, suppose we denote x1, it should transform to itself. So if we subtract this, the error should be 0. We use another Ransack, because all of them are randomly selected. So we do several iterations. So we do several iterations, find the smallest error when subtract the transformed x1 with the original x1. We use the smallest as the result. As you can see, it's still not perfect, but it's the best one we can find. So this and we have other experiments. This is merged or fused by 3 different models, and this is an indoor experiment. This is all lab. It's from 10 models, and there's some video results about the protein. And this is the bottom one is the track field. This is also this one is also merged by 8 supermodels. So to conclude our work, we provide a way to turn video surveillance in 3D, and we reduced the image matching time compared to the traditional structural motion. And we also we proposed the angle image method to accurately stitching the supermodels together. And for future works, we would like to improve the avatar figures in the 3D surveillance to get more real feeling of the surveillance. And as you can see, the 3D model is not perfect. It still has a lot of holes, so we would like to dense the safety features. And it might be better to digitize more of the buildings in the world, and to do more 3D tourism applications. Thank you.